Hello everyone, I'm Mary Wright. I'm director of the Sheridan Center for Teaching and Learning. And excuse my allergies today, it makes my voice very scratchy. So I'm very happy to be here today to facilitate a panel on applying scientific research. I just read a paper this morning that talked about the importance of communicating our results to the public in a better way. So this is a really timely topic. So the format that Clayton, Gabriel, and Anna and I have talked about is that I'll introduce each person, and then they'll present for 15 minutes. And then we'll have about 5 minutes for Q&A particular to that session. So we'll do that 3 times, rinse and repeat. And then in the final part, we'll have another period of time for discussion and Q&A, where we'll really try to synthesize the 3 presentations and put them together. So our first presenter, going in order of the program, is Anna Schwartz, who will be presenting on the effects of timbre distortion and arousal on memory for vocal and instrumental melodies. And she's been advised by Elena Festa and Peggy Chang in the audience. So let me first introduce Anna, and then you'll be able to hear her present on this topic. So Anna is a music cognition concentrator graduating in May. Congratulations, Anna. She's a passionate musician as an oboist in the Brown University Orchestra who desires to pursue clinical neurology. And since her sophomore year, Anna has conducted research with professors Elena Festa and William Heindel in the Aging and Cognition Lab to understand the differential factors, such as emotion, that impact memory for vocal and instrumental memories. So thank you, Anna.
Thank you. Good morning. Thank you so much for the introduction. My name is Anna Schwartz, and my thesis is titled The Effects of Timbre Distortions and Arousal on Memory for Vocal and Instrumental Melodies. So I'll present some of the background that has formulated my thesis project. There are differential behavioral responses to vocal and instrumental melodies. So studies have shown that vocal music induces higher levels of arousal as well as better recognition memory performance. So taken together, these findings suggest that there is a distinctive auditory processing mechanism for vocal music that is modulated by arousal level. Additionally, studies have shown that when you distort surface features of instrumental melodies, that impacts memorial retrieval of those melodies. So surface features of melodies include things such as timbre, which is the musical instrument, key, major and minor keys, and tempo, so how fast the melody is played. So when you change those surface features, you're not changing the identity of the melody, just certain aspects of that melody. So what those studies have found is that that timbre is actually more tightly bound to and consolidates with the memorial representation of those instrumental melodies as opposed to tempo and key. So taken together, I was able to formulate my own research questions. So the first one is, are memory representations of vocal melodies different from instrumental melodies in surface feature binding patterns for timbre? Second, I'd like to know if arousal level and spatial orienting impact memory performance for vocal and instrumental music memory in similar or different ways. So overall, the purpose of my study is to compare memory recognition performance in healthy young adults for vocal versus instrumental melodies with timbre distortions over a short time delay. So the overarching question is, are there similar melody memory impairments with timbre distortions for both vocal and instrumental music? So this is a schematic that I used to create my musical stimuli that were used in this study. I had 48 musical excerpts, and I created the stimuli based on country of origin, British or Irish folk melodies, and this was so that the melodies were unfamiliar yet maintained Western tonality. We also used major and minor keys as well as duple and triple meters. I conducted 4 experimental trials for my thesis. The first two experiments, we compared implicit and explicit music memory for vocal and instrumental music in the context of timbre distortions, and we really didn't find any significant differences in accuracy for memory performance. So for the purposes of time, I'm going to focus on experiments 3 and 4 of my study. In experiment 3, we assessed explicit memory of instrumental and vocal melodies using a 7-point confidence rating scale, where 1 represents that the participants were confident the melody was old, to 7 meaning that they were confident the melody was new. Experiment 4 was very much similar to that of experiment 3. We used a 7-point confidence rating scale as well, but in addition, we implemented an old-new judgment task where subjects were asked to indicate whether the melody was old or new by responding to 2 buttons that appeared on the screen that said old or new. So this is the overall setup of each experiment. There was an exposure phase, a covert-oriented task, and then a test phase. So in the exposure phase, participants completed or listened to 24 melodies that were in vocal and instrumental timbres, and the task was to indicate whether the music was happy or sad. So the covert-oriented task was completed next. This serves as a 10-minute filler task between the exposure and test phases, and what we were able to acquire from this was indices of arousal and spatial orienting, which are both components of emotion. And then in the test phase, participants heard 24 new melodies as well as 24 old melodies in vocal and instrumental timbres. Half of the old melodies that were presented were distorted by timbre. So, for example, if a piano melody was heard in the exposure phase, they now heard it, the same melody, but in voice, and half were unchanged. And the task was to determine if the melody was old or new, using that 7-point confidence rating scale, as well as the old-new judgment task for experiment 4. So this is the demographic information for the participants that participated in experiments 3 and 4. We acquired information on gender, on age, education, as well as music experience. So what we were able to find is that there were overall more proportion of happy ratings for major than minor melodies, as you can see on the left hand of the graph. Additionally, you can see that there's a greater difference in the difference of the major and minor piano melodies than there is for vocal, which suggests that not only were people more accurate in distinguishing major and minor keys for instrumental melodies, but that people perceived vocal timbres to actually be more happy. And we were actually able to replicate these findings in experiment 4. The recognition phase of experiment 3, we were able to find certain important findings. First is that, as you can see, the red bars represent the piano melodies, and you can see that those are all for all 3 conditions of stimuli: new, old, different, distorted by timbre, or old, same, that they were all more perceived as new. So there was a preferential bias to identify piano melodies as new. Additionally, we were able to find a significant difference in the old, different, and old, same average ratings for the piano melodies, which suggests that timbre distortions of instrumental melodies are detrimental to the memorial retrieval of those melodies. However, that significant difference for the old, different, and old, same vocal melodies, as you see in the blue bars in here and here, you see that those are not significantly different, which suggests that that timbre is actually, the distortion is actually not that detrimental to the memorial retrieval. This is the results that we found for the recognition phase for experiment 4. We were able to replicate the findings for the piano melodies. However, with vocal melodies, we can see in the old, different, and old, same conditions that there was a significant difference in the average ratings. So that suggests that in this condition, there was actually a detriment to memorial retrieval for old, different, and old, same vocal melodies. Now this graph represents the additional old, new judgment accuracy task that we acquired in experiment 4. What you can see here, what's really most important, is that in the old, different condition, both the accuracy proportions for vocal and piano melodies those are both below chance level. So that suggests that timbre is actually very much associated with the memorial representation of vocal and instrumental melodies. We also see patterns of a preferential bias for piano melodies to be recognized as new and for vocal melodies to be perceived as old. We also completed some preliminary correlation analyses with the arousal and oring indices that we acquired from the covert oring task. And what we were able to find in experiment 3 was that greater arousal indices were associated with better recognition performance for new vocal melodies as well as music experience. We also found that greater oring levels were associated with poor performance for identifying old piano melodies. Contrastly, in experiment 4, we found rather different findings. We found that greater arousal indices were associated with poor performance for new piano melodies, as well as distinguishing new and old same vocal melodies. Additionally, we found that greater oring indices were associated with better performance for new and old different piano melodies. So while we found very different findings for experiments 3 and 4 with the correlations, we can acquire this to the fact that there may not have been enough power in those correlations. So in the future, we would like to acquire more subjects for our studies. Additionally, we hypothesized that perhaps we presented too many melodies to the participants, which could have increased the difficulty of the task, which could have led to very different findings in our correlations. So taken together, we can conclude from these findings that changes in timbre do affect memory recognition for unfamiliar instrumental melodies, but not as much for the vocal melodies. And these findings may be due to arousal and oring levels that are associated with memory recognition. So altogether, these findings do suggest distinctive auditory processing mechanisms for vocal and instrumental music. So other questions that we have from this study is that we'd like to see how the surface feature binding patterns compare for vocal and instrumental melodies with other surface features like key and tempo, and for other time delays between exposure and test phases, such as 1 day and 1 week. And then in association, how arousal and oring levels impact memory performance in those conditions. Additionally, we'd like to see to what degree memorial representations of melodies are affected by neuronal atrophy associated with aging and dementia. There's a lot of the literature that suggests that music processing is intact in patients with Alzheimer's disease and healthy aging, despite cortical atrophy and atrophy associated with aging. So we'd be curious to see how those patient populations would perform with this task. And finally, I'd like to thank my advisors, Elena, Festa, and William Heindel, for supervising this research and for being my concentration advisors. They've been integral to my education here at Brown. I'd also like to thank Julie Strandberg, who has been a professor for 2 of my courses and is also a reader of my thesis. I'd like to thank Dean Peggy Chang and Dean Rodriguez for supporting me with my pursuit of developing an independent concentration and creating such a personalized course of study. Thank you.
I think if you want, you can sit down and take a break and then field questions. So the next 5 minutes, we're going to take some questions for Anna. And I'll ask the first one, which is, could you, given the title and framing of this session, could you tell us about what you think at this point in time are 1 to 2 practical implications of your work?
Sure. So I feel that this can be very informative for developing clinical music therapy practices for patients with Alzheimer's disease and for other neurological disorders. I think because it sheds light on the influence of arousal and preferences for perceiving and interpreting music. I think it shows that we all respond to different forms of music very differently depending on our preferences for vocal or instrumental music. So I think it shows that in terms of creating a list of music that you would use in music therapy practices, that it needs to be very individualized to the patient that is receiving that therapy.
That's great, thank you.
Yeah, of course.
Are there other questions for Anna?
How did you go about, or could you just describe the type of prompts you gave for the vocal and the piano? Like, what was the genre? What were the vocals, groups or individuals, or was there a cultural? I mean, you said British and folk, so could you just?
Yeah, sure. So we used British and Irish folk melodies specifically so that the melodies would be unfamiliar to the participants. We didn't want any memories of familiarity to influence performance during the task, but we also wanted to maintain Western tonality of the music so that participants would actually enjoy listening to the music. In terms of creating the stimuli, we used a synthetic computerized program called MuseScore 2 that we may, in the future, want to get live recordings of piano and voice, just because it's possible that for those that do have a stronger music background that participated, they may have thought that the music didn't sound genuine enough, which could have influenced arousal, spatial orienting levels that we acquired in the task. Yeah, absolutely.
It's actually a good segue, because I was curious as to whether the participants were screened on how much or if they had music background experience.
Yes, they completed a post-test questionnaire at the end of the study and we asked them all about their music background. Have they received music lessons, voice lessons, music theory lessons? Are they currently engaged in it? If not, when did they stop? We also asked if they implemented any strategies in throughout the exposure and test phases to see if any explicit strategies would help in terms of memory retrieval. So we did all of that just because the literature does show that music background does influence music processing tasks. So we wanted to see whether music background had any influence on performance. And what we did find was that greater arousal levels that we acquired in the covert orienting task were positively correlated with music experience. So the more music experience people indicated, the more arousal they had throughout the study. So, yeah.
So we have time for one more question if there's another one. Okay, so maybe one will surface at the end. Thank you so much for kicking things off, Anna. So next we have Gabriel Rays, who's going to be speaking about neural correlates of racial bias and discrimination, and he was advised by Monica Linden. So Gabriel is a native of Albuquerque, New Mexico, who is graduating this May. Again, congratulations to you, Gabriel, with a concentration in cognitive neuroscience. So he is one of the lead coordinators for the New Scientist Collective, which is an organization at Brown aimed at supporting minorities in science. And he is a passionate proponent of diversity and inclusion in science. So Gabriel aspires to attain a graduate degree in cognitive neuroscience and education. And I will just take this opportunity to do a bit of self-serving product placement in that Gabriel is a student in Dr. Christina Smith's Theory and Practice of Problem Solving course. So this might be a course that you're interested in enrolling in the fall or spring too. So I'm going to pass around this bit of information, and then Christina can speak with you if you want to know more. So thank you, Gabriel.
So thank you, Mary, for that introduction. And hello, everyone. Again, my name is Gabriel, and today I'll be talking about one of the group independent study projects that I did this semester that looked at the neural correlates, again, of discrimination and bias. So just to kind of get started, I think that it's one of the reasons that we were interested in exploring this topic is because a lot of the current events that you'll see today really highlight the fact that discrimination against people of color is very much still prevalent in our society today. So one way that you can think about it is that evidence has indicated that people who have black sounding names are less likely to get interviews versus white sounding names. It's also a hot topic in which black people are disproportionately targeted by police in our current society. And then even recently, right, with the Starbucks incident that occurred just a few weeks ago with Black men who were arrested for occupying the space. So very much this demonstrates the fact that there is still definitely bias against minorities in this world. But in addition, there is also several initiatives that are trying to combat this, right? So there's affirmative action and other initiatives that are attempting to diversify academic and corporate spaces. You also have movements like Black Lives Matter that are trying to draw attention to the realities that many Black men face with regards to police brutality. But even in addition, this month there will be a mandatory Starbucks bias training that all the employees will have to undergo in order to sort of react to what happened. But we wanted to ask, like, why, despite all these efforts that have occurred for several decades, it's not enough and that we're still witnessing all these egregious acts of bias. And so that led us to want to explore these neural markers of discrimination to see whether or not it would elucidate our understanding of how this arises in the first place, with these three questions that we had in mind. So the first was generally looking at what the neuroscience literature has to say with regards to this topic. And we also wanted to look at how these experiments are being carried out, because we wanted to know what exactly are they trying to explore and what message they're trying to send, and whether or not they're simply looking at correlative measures or whether they're actually trying to figure out how to diminish implicit bias. And then lastly, we also wanted to know whether the experiments that we read from the neuroscience literature, whether that informs our understanding of how to combat these implicit biases. So just to give you a quick rundown of how we engaged in the course, we spent the first several weeks just kind of giving ourselves a foundation to discuss and go over the events and the history. And then during week 3 is when we actually got down to the nitty-gritty of the course. So we spent the first couple of weeks just familiarizing ourselves with the methods used in neuroscience and in cognitive neuroscience. And then we spent the next 3 weeks looking at particular regions in depth that have been implicated to be associated with bias. And then we spent the next weeks looking at how this is applied to society in terms of can we diminish and can we teach people to learn to lose implicit bias. And then we spent the last weeks looking at developmental cognitive neuroscience. So what does this look like for children and when does it start manifesting? So today I want to particularly focus on the IAT and one region in particular, as it was one of the most pervasive methods utilized and one of the most regions constantly implicated and cited with regards to the literature. So we'll focus only today on looking at the amygdala and the IAT. And so for those of you who are unfamiliar with the implicit association test, it's a very popular psychological tool that captures implicit bias by trying to draw these associations in concepts by looking at the participant's reaction time. So kind of give you an example of what that might look like. A participant who takes the IAT will first be exposed to one concept. So here, they're going to be looking at several words, and they're tasked to determine if the word makes them feel pleasant or unpleasant. And so what you see here is they'll press left if it's pleasant, right if it's unpleasant, and then you'll see a series of words, and they're just going to have to categorize them during the task. They'll then switch it to another concept, in which now they'll look at names, and they'll have to associate that whether it's a black-sounding name or a white-sounding name, and make the same categorization. So left if black, white if right, and then they'll see a few just to prime them for the experiment. But then what the IAT actually looks at is now these associations. So now they're going to be tasked to determine if it's left, if it's black or unpleasant, or right if it's white and pleasant. So they'll only be exposed to one stimulus, but they won't know which one is coming. It'll be completely random. So here you'll see a name, and they're tasked to determine if it's a black name or a white name, or they might see a word, and what's going to happen is they'll have a block in which they'll now switch it. So what you saw here was what's considered a congruent trial. So typically, black stereotypes are associated with unpleasant characteristics, and white stereotypes are associated with pleasant characteristics. But then an incongruent trial is when you have the inverse, where black is associated with pleasant words and whiteness is associated with unpleasant. And typically, the hallmark of the IAT is that there is this dissociation in reaction time between incongruent and congruent trials. So normally, participants are a lot faster at making an association between congruent trials, so associating whiteness with pleasantness and blackness with unpleasantness, and a lot slower at associating incongruent trials, so associating blackness with pleasant words, for example. And so we saw a lot of activities that looked at the IAT to sort of capture implicit bias, and this was complemented by a lot of fMRI studies. And so one in particular that we'll look at is a paper by Elizabeth Phelps at NYU. And so what she did is she had participants now use functional magnetic resonance imaging with just a brain imaging tool to look at neural markers, and had participants do the IAT that was a race-based and word-based task, as you saw previously. And what she found was during the incongruent trials, there was an association with the amygdala part of the brain versus congruent trials, and that these incongruent trials are specifically looking at black and pleasant. So there was a lot of literature that has been replicated to actually find that this region has been associated with the IAT with regards to race. However, a subsequent study that we wanted to look at now was whether or not that this can be diminished by our understanding of how the amygdala works. And so a subsequent paper that we read after the Phelps paper was looking at propranolol. And then what this paper highlighted was that because the IAT had shown an association with the amygdala, previous papers have found that propranolol actually diminished activity in the amygdala in other studies. And so what the authors here wanted to look at was whether or not participants who were in the propranolol group would show a diminished implicit bias on the IAT if propranolol is associated with the amygdala, and if the amygdala is associated with implicit bias attitudes towards people of color. And so their hypothesis was that the use of propranolol would actually diminish the implicit bias without diminishing the explicit bias. And what you can see here from the results was, first looking at the placebo group, so it's the black line there, you do see the hallmark of the IAT, so you see that participants are faster at associating congruent trials versus incongruent, but with the propranolol group, which is the dotted line, they did not find a significant difference between the congruent and the incongruent, which supports the hypothesis of the authors that there was a diminished implicit bias if you interfere with the amygdala pathway of the brain. And so one further paper wanted to suggest that the amygdala might be responding to these people of color as a threat perception. And so they argued that the amygdala is a reflection of threat-based perception of black people. And so there was evidence to support this by looking at subliminal priming and eye gaze and fear conditioning. And one paper that I wanted to talk about more specifically was a paper done by Trollwalter and his team. And so what they did here is they wanted to see what would happen to participants if they were subliminally exposed to people, to faces of different races. And the reason why is because a lot of evidence in fear literature had found that if participants were exposed to intrinsically fearful stimuli, such as spiders, it would cause a heightened arousal in their body to cause them to react faster to the task, whether they were aware of this or not. And so what the participants here were exposed to was to first stare at a cross, and then they would be exposed to faces on both sides of the cross that would be either a white face or a black face, and they would be the exact same face. But the face would be shown very quickly that the participant was not conscious that this face was actually presented. And then what they were supposed to do is to determine whether there was a dot to the left or the right of the cross. And what the researchers in this task wanted to explore was whether or not there would be a difference in reaction time between black faces and white faces, if it was consistent with the fear literature and if it was supporting this threat-based perception. And what the researchers did find was that participants were significantly faster at responding to the dot if the face was black versus white, which is supporting their hypothesis and supporting this theory that there is this threat perception. But I do want to also highlight just very briefly on like this conversation some of the limitations and the recommendations. And the first would be the fact that these papers primarily only looked at participants who were either white or black. And so we definitely recommend that future studies should definitely look at more diverse participants. So what does it look like for Hispanics to do the IAT? What does it look like for Asian Americans? But we also wanted to explore the disparities in gender because normally the stimuli did consist of the use of black men. And so we wanted to know what would this look like if they incorporated gender components. So now if they included white women and black women, but also of other races as well. And in addition, I think it's also really important to highlight the fact that these results can also be skewed depending on where the experiment is performed. Now, if you look at Brown, for example, it's an incredibly liberal campus, and many of us might be more aware of these implicit biases and of the realities that many minorities inhabit. But if you look at more conservative spaces that may not exactly have these sort of rhetoric or initiatives or ideologies that pervade their campus, it might also interfere with the results and thus not exactly capture what the overall population is demonstrating. Furthermore, we also think it's important to incorporate more cognitive neuroscience tools to sort of disrupt regions that have been implicated. So one example is transcranial magnetic stimulation, which has been used a lot in neuroscience literature to sort of interfere with neural activity. And then the last component is also just questioning the IAT itself, because it is the most popular tool to capture implicit bias. And the reason why is because we wanted to know whether there was another measurement that can also capture implicit bias, because it's unclear whether or not that this is actually capturing anti-POC sentiment or if it's actually capturing pro-in-group sentiment. Additionally, some people might be more familiar with the experiment, so it's now a question of whether the IAT is actually capturing implicit bias or if it's just capturing one's ability to perform the task. And yeah, I think those are all for me. So my acknowledgements is I want to thank Dr. Monica Linden and Dr. Jalonia Dent, who were the sponsors and supporters of this. In addition, I also want to thank all of my course mates who helped create the syllabus of the class and provide their own perspectives. And then lastly, Dr. Peggy Chang for helping out with the GISP and being very supportive in the creation of it. So that is all for me, so thank you.
Thanks, Gabriel. That was great. So one challenge of public science is thinking about how your results might be interpreted or misinterpreted. And I know, Gabriel, before this, you were talking about the potential interpretation that people would read this and say, people are racist. And I'm wondering if you could speak more to how you would handle that.
Yeah, I think it's definitely important to highlight that many of the studies that look at behavior and in cognitive neuroscience is extremely correlative. So this doesn't necessarily mean that anyone who has activity in the amygdala or even has an implicit bias against another person that it's definitively racist or that they're bad people. I think it's really important to remember that correlation doesn't equal causation. And so I think that it's very important to also look at this in context, because I do think that it's a consequence that if this were to be published, for example, or if these studies were sort of publicized in a major article, that there is a possibility for people to sort of read this and be like, we have neuroscience evidence that the amygdala is what causes people to be racist, and if you have participants that show amygdala activity, that means they're bad people because they hate black people. And I think it's really important to remember that these are merely looking at associations and patterns and not necessarily making definitive marks.
Thank you. Are there questions for Gabriel?
You talked about the liberal conservative bias, but you also said the test was developed at Harvard. Perhaps not as liberal as Brown, but quite close. At least in the popular reporting of that test, the point is that there's no difference, right? Even at a place like Brown, even with people that sort of have some level of education on this test, other than propranolol, there's not what strategies other than propranolol can you use to kind of get better?
To get better at the IAT?
No, to address the implicit bias that is driving the results of it. What in the class did you find, what strategies do people use? Are there any strategies that people have used successfully other than drugs to kind of address implicit biases in ways that show up in this metric?
Yeah, I would say that even the IAT itself has been kind of controversial because there's a call in question about its reliability and the validity of it. So reliability meaning whether if someone else were to take it again, would they get the exact same result? And then the validity talking about, is it actually capturing implicit bias? And so even the IAT itself, just as a tool, has been brought into question by many psychologists. But to answer your question in terms of other strategies, there are certain papers that have suggested ways to mitigate implicit attitudes. During our developmental section, we looked at children who did a version of the IAT that was tailored towards them, and they wanted to look at whether representation of minorities or whether individual relationships with minorities would have an impact on implicit attitudes. And what they found was actually having individual relationships with people of different races was able to sort of mitigate the implicit attitudes compared to just mere exposure. And so I would say that that could be a potential follow-up to look at now what does that look like for adults. And I think that the component also with looking at liberal and conservative spaces is that Brown, you have much more exposure of that representation of people of color. And that I think can also lead to more individualized relationships. And so when you have a campus that might not be as diverse, but also may not be as inclusive to those backgrounds, I think that can also be a major, major distinction. To look at to see whether or not it's similar or whether there's more exaggerated results. But yeah.
Other questions?
Throughout creating the syllabus for your GIS, what were some challenges that you all faced as a group, and then how did it carry out throughout the semester?
Yeah.
Because it seems like there was a lot of things to cover, but then knowing the scope of it being one semester, how was that like?
I think that one of the major challenges is that there's not a substantial amount of literature that addressed all of the questions that we wanted to. So I think that we had to make, I wouldn't say a lot of stretches, but we definitely had to sort of really read papers in depth before actually reading them in the class to see whether or not it would be a paper to explore. Because I think that one of the things that we noticed is that some papers were misleading. So they had a title where like, we're looking at IAT and race, but they didn't actually really address any of the questions that our course was looking at. So I think that that was something that we kind of did while we were like looking for our readings. And I think the other challenge as well was like some papers were published, but they doesn't necessarily mean that they're like good experiments. And that was also one of the things that we wanted to learn, because even if they're not good experiments, if a non-lay scientist were to access them, they would use the fact that it was published in a journal as like enough validity. And so that was also one of our challenges, like, are we also equipped enough to catch these? Or would we also be biased to like interpret the results as very meaningful, even if the experiment itself was not very good? And so I think that was also a challenge that we constantly went through every week when we decided on readings.
Okay, thank you again. I think we're going to move now to our third presenter, Clayton Sanford, who's going to be speaking about robust and bounded machine learning. And Clayton was advised by Eli Upfal and Michael Littman. So his brief bio is that he is an applied math and computer science concentrator, graduating also in May. So my congratulations to you too. For the past year, Clayton has researched machine learning with computer science professors, Michael Littman and Eli Upfal, and he wrote a senior thesis about that research. After graduation, he plans to return to California. Wonderful. To work as a data scientist at LinkedIn and escape Providence's cold weather. I like it. I like how you think, Clayton. So let me now welcome Clayton for our final presentation.
Hey everyone, I'm Clayton, and today I'd like to talk a little bit about the senior thesis I worked on this year with Eli Upfal and Michael Littman. So the focus on my thesis was on essentially statistical bounds on machine learning. And what I'd like to do is I'd like to kind of zoom out and figure out, kind of explain this from nothing. So we can just like explain what machine learning is, and then we can get to what my thesis is. So machine learning is a process by which we use algorithms to gather insights from data. So in particular, you have some algorithm, you're given data, and then you can come up with patterns or make decisions based on those data. So one common application of machine learning is image recognition. So for instance, here, you're able to give photos to Google, and Google can figure out that this is an orange, this is a banana, this is a TV, things like that. And the way it does that is that you first give it a bunch of other images like this with these things already labeled. And then Google's algorithm has some form of network which learns patterns. So it learns what characterizes bananas, what characterizes oranges, and so forth, so that given new images that it hasn't seen labeled, it can then predict those labels. Another popular application of machine learning people like to talk about are self-driving cars. So self-driving cars, the algorithms that pilot self-driving cars are built on enormous quantities of data because the cars have sensors and are constantly gathering data about the environment. And they need to figure out, based on certain weather conditions, based on images about where their cars are, about how they're going to navigate. When do I accelerate? When do I turn? Things like that. So you have these, so machine learning algorithms have developed tremendously, and as they've developed, they're being applied to domains that really matter a lot more. You know, like when we're talking about things like this, like it's kind of fun to be able to identify things, but once we start talking about using them for things like self-driving cars, where personal safety is at risk, and where it could also like fundamentally change the fabric of how society works, it really matters that we get this right and that we don't make a lot of mistakes with it. So what I want to do is I want to go over a few kind of risks of machine learning, and then I want to hone in on the thing that I've been working on in particular. So one thing which concerns people about machine learning is the privacy aspect. So machine learning, as I mentioned earlier, requires an enormous amount of data in order to make conclusions, and that data has to come from somewhere. The reason why Facebook and Snapchat and so forth are free is because we're giving them tons of data, and then they can convert that data into making algorithms, which then in turn can help them profit. And there are a number of implications of that. one of which being that your data aren't always safe. With things like the Equifax hack that happened this year, people unknowingly had given their data to this company and someone hacked it and then had a bunch of personal information on them. Another key danger with a lot of machine learning and a lot of this focus on big data is that there can be tremendous bias built into these algorithms. So for instance, often because the algorithms are based on data and because historical data are skewed by prejudices or historical injustices, those same biases might likely be reflected in the outputs of the algorithm because they're based on what they take in. What I'd like to focus on today is another issue which I see is very important, which is an overconfidence in machine learning. So people not knowing when algorithms are going to work or when they aren't going to work. And the goal of my research is to come up with better ways for us to know why an algorithm will work or how much data we need to ensure that an algorithm works. So I think all of these are incredibly important things, and I'm actually happy to talk about any of these during the Q&A after, but today I'm going to hone in on overconfidence and that being a problem. So one of the things which is true in machine learning is that often we learn algorithms which produce really good results, but if you tweak the inputs a little bit, you can get really bad results. So one of the things we can notice here is that all these things on the left were identified correctly by some image network. So like it said that this is a dog, it said that this is a school bus, etc. But then we found that we could add, if you add like just a little bit of static to it, all of these are classified as ostriches on the right. The images don't look any different, but somehow these are all ostriches. This is not a dog, this is an ostrich. So these algorithms, like in general, when you give it image data, it normally performs really well. But if you choose just a clever way to mess it up, you can get these really horrible results. So there are a bunch of key issues there we have to work out. So the goal of the general field I've been researching in has the focus of coming up with ways that we can use mathematical bounds to ensure more correctness in our machine learning algorithms. So essentially what we want to come up with is we want statistical error bounds that say things like 95% of the time our error will be no more than 5%, something like that, so that we can actually be confident in our algorithms and not just use a justification that, well, this algorithm worked in the past, so it's going to work now. And then we want to see, okay, we have these bounds, but we also have to bridge the gap between theory and practice, and we have to find a way to make bounds that are computable and useful enough that people can actually use them in industry where these algorithms are being developed. This is a very broad field, so I'm going to hone in on a little piece that I worked on. And what my main goal was to broaden, there's a certain kind of complexity, which I'm going to talk about in a bit, and I attempted to broaden the range of problems that we could apply that to. And then I also tried to apply that to certain kinds of learning problems. Today I'm going to focus just on the theoretical stuff. I'm happy to answer questions about the applications I worked on, but I mostly just want to go over the theoretical framework that I worked on with my grad students, or with my grad student mentor. So the core problem we're working on here is solving a kind of error that comes from something called overfitting. So overfitting is the process. Overfitting happens when a statistical model essentially memorizes the data you give it without learning any kind of underlying trend or pattern. So here's a problem which is pretty typical in machine learning. It's a regression problem. And what you're trying to do is you're trying to predict this orange plot. And to do it, you're given these blue points, and we're saying, okay, let's come up with a function that best approximates those blue data points so we can estimate the orange thing that generated them. And what you have to do is you have to choose what kind of model to use to fit those points. So for instance, one of the simplest models to do is say, okay, I'm going to pick a line and choose the line that best fits those points. And what you get is you get the plot on the left, where, okay, the line kind of sort of gets where the data goes, but it really doesn't get any of the actual curves of the data. It just gets the general direction. One of the best estimates for this would be if you choose, in this case, a fourth degree polynomial. And if you notice, the blue curve and the orange curve are almost exactly the same in this one. So when you pick a fourth degree polynomial that fits the data points, then you hit almost all the points and you do really well. The overfitting issue comes into play when you pick a really high degree polynomial. And what happens here is the polynomial kind of swerves to hit all the data points, but it doesn't actually get at this underlying curve. So for instance, if I were to say, what's the value, what do you predict the value here to be? It would say something way down here, even though it really should be trying to follow the line. So what happens is when you use these models with more degrees of freedom, like here, you need a lot more data than you need for this. And these bounds come into play for figuring out how much data we need for these different types of complexity. So hypothesis complexity is one of the things that I worked on measuring, which is roughly coming up with a way to think about how expressible a hypothesis is. So given a way of labeling data, how likely is it that my hypothesis is going to be able to fit those labels? And in particular, I looked at Rademacher complexity, which is a measurement which focuses on essentially it essentially measures the ability of a hypothesis class, or of a set of machine learning kind of solutions to correlate to some data distribution that you're drawing. And the problem I worked on in particular was the denoising problem. So the general goal here is you have an image, you apply some form of static or noise to the image so that it's like blurry in some way. And then the actual algorithm is you try to take this noisy sample and get some form of cleaned output where you remove the static from it. And to do that, what you do is you give it lots of pairs of clean images and noisy images, and then essentially I tell it that this is the correct version of it, and then I try to learn an algorithm that gets this to something close to that. And in general, a sensible learning approach to this would be to say, okay, I get some images, I get some pieces of static, I combine them together, and then I learn on these pairs. So the problem is that machine learning algorithms require a lot of data. And in order to get enough data here, essentially every data point I need for the algorithm, I need to get a new image and a new piece of static. And in a lot of ways, that's really inefficient. What would be better would be if I could make some combination like this, where essentially I say, okay, I'm going to get this lion image, and then I'm going to combine it with every type of static I have. And then I'm going to take the flower and combine that with every type of static. So that way you end up getting many more data points to feed into your algorithm with less data collection needed at the beginning. The problem is that previously, the learning bounds and guarantees I was talking about only apply if you have a case like this. So the main contribution of my research was making it so that if you had a framework like this, you could apply those kinds of bounds. So we want to see if we can make our bounds easier to compute, because as we're looking more into applications, and we want to find other domains besides audio denoising where we can apply those bounds. Also, this is a very specified part of the field, so we want to see what people in other parts of the field have been doing, and we want to see how we can compare our bounds with theirs. I'd really like to thank everyone who's helped make this project possible, including my advisors, my reader, the grad students who helped me out, and all the people who helped out with editing, including Jacob, who's in the audience. Great, thank you.
Thanks, Clayton. So we were just talking a question about thinking about interpretations of your work for the public, and so I have a different dimension on this, so I'm hoping you can give me some advice, Clayton. So I do work on educational research. I do it in classrooms. Now, people typically, when they think about methods of research, they're familiar with things like Anna's great presentation, lab research, or the lab studies that Gabriel talked about, but the classroom is really messy. It's real life. And similarly, you're using mathematical methods that are very concrete to apply to the world, which is very messy. And so how do you make sense? How would you be able to explain your methods in that? How can math possibly explain all the possible outcomes that could happen in the world?
So that's a really good question. And I think first I want to address that I think one of the reasons why we have problems in machine learning is because a lot of people don't really understand the underlying math and have kind of too much faith in the belief that math is somehow objective and that there aren't assumptions baked into mathematical models. So, for instance, one of the things which every kind of mathematical or machine learning model requires is making assumptions. So, for instance, in the image recognition, when we're doing the image recognition task, you need to assume which kinds of things are important to recognize. You need to know that, like, the banana's valuable to recognize, but the bowl is not, or something like that. And because the mathematicians who make these models need to make assumptions, that means that, yes, these models don't capture all the things that can go wrong in the world perfectly, because the models are inherently a simplification of the real world problems. So in a domain like education, it's particularly tricky. I've actually read a bit about issues where teachers will be evaluated on, where teachers will be hired or fired based on the testing data of how well their students perform as compared to how they did last year. And one of the big statistical problems with that is that it's just too small of a sample size. It's too hard to judge. It's very hard to judge whether a teacher's good based on just like the test scores of the students year to year. And the thing that needs to be talked about is that there's an unspoken assumption there, which is that the things that are valid to evaluate teachers on are just these test scores. So maybe even if the math component is objective, the part leading into the math component where we say these are the things we're going to consider is not objective. And that's where there needs to be more dialogue, and where we can't just have the mathematicians making the decisions. That's where we need to have social scientists being involved as well.
Thank you. That's a great answer. Here for the social scientists. Are there other questions for Clayton?
Yes?
Building off of that, so I was listening to a recent NPR story about fake news and the way that people can create images or auditory or even movies at some point that can, potentially be problematic in the sense that they're not true necessarily. So within that context of your research, what are the ethical implications of your research potentially in this new era of fake images or fake audio or video things, and how might it be used in that space?
So I think one thing I want to highlight first is that also some cool applications of machine learning are actually working on combating that. So I actually have a friend I know who's working on a startup that uses machine learning to try to identify fake news based on things that are said in the article, and basically comparing it to articles that we know are legit and articles that we know are not legit as a way to kind of classify off the bat if we think something's fake or not. So there's definitely, I think it's, it's a technology and it's a tool that can be used kind of either way. But your question is about whether kind of the ethical implications of this, and I think with the small slice I did, I think the main thing this changes is trying to add a little more precision to results. So trying to figure out, how confident should we be in these. But I think with a lot of other machine learning research, there actually is a lot of work being done on like basically how to make things like images from scratch, which in some ways is really cool, but also, these technologies possibly could be used to to help create fake news or help create misleading images. So I think it's, I guess I don't promise to have all the solutions, but I think one thing that I think is very important is that we figure out a way to kind of value our data more, because our data is what makes these models possible. And if people, as long as we as a public don't value our data very much and are kind of okay with companies collecting it from us, we almost shouldn't be surprised that they're able to develop models like this that are able to predict what we want to do or come up with forgeries or things like that. Good question.
We have time for one other question if there's one.
Julia?
How confident should we be? Like, what was the application? I mean, are we wildly overconfident? Are we wildly underconfident? Like, what did you find in the applications that you did? Wow.
So, I haven't. So I think at the end of the day, it's a domain question. So I think I would want a lot more confidence in my self-driving car than I would in my image recognition. So I think at the end of the day, it matters. It really matters like who's going to be implicated by this. To think about how much confidence we need. I think the main difference is I think that a lot of the main aim of my research is broadening the number of things where we can create confidence bounds at all for, because I think often people have the tendency of just using the algorithms, observing that they work well, and continuing to apply those algorithms. And my goal is to increase the number of tasks where it's actually feasible to do this kind of confidence analysis, so that you can at least have something. You can at least have a baseline level of confidence, rather than it worked well in the past, maybe it'll work well now.
Okay, thank you. I want to pivot a little bit and then think about putting these three presentations together and thinking about some of the synergies or critical differences between them. So I'm first going to invite the panelists to identify what do you see as some of the resonances with your co-presenters. Clayton, do you want to start?
Sure. I think one of the things I think that one of the things we identified when we were first talking about the commonalities we had is that we all kind of dwell on the line of technologies or ideas that have been kind of worked on in the lab that haven't really yet been fully applied to society, and that we're all kind of thinking about, we have these cool works, but we could see ways that the applications could not follow through in the way we intended. So for instance, with Gabriel mentioning how, being able to more reliably track where racist attitudes come from could also have negative externalities, or especially with mine, where, adding more tools to the machine learning toolkit, creates advantages but also disadvantages. So it's kind of, we're all kind of on this line where we've been working on things and maybe they'll be applied, but we don't really have confidence in what the applications are going to look like yet.
Great. How about you, Gabriel?
Yeah, kind of to add on what Clayton was saying, I definitely think that many of us and our interests are still very much focused on the theoretical aspects, like exploring, like out of our own general curiosity, like some of the things inspired by society and what's currently going on, and trying to use the scientific component to sort of address those things, with ultimately the intentions of one day applying it to society and hopefully informing us like how we should sort of navigate in the world. And I think it's like one of the things that all of us might face in the future is the fact that like if our like access to our research might actually unintentionally and inadvertently apply it to society anyways, even if we're not ready. So I think having these kinds of conversations and like thinking about the ways in which science is actually integrating into society slowly but surely is like a common thing that I like saw. So mine focused on like social behavior, Anna's focused on music cognition and illness, and then Clayton focusing on like the emergence of tech and AI and machine learning. And I think all of these things are very much like necessary topics to explore and further investigate to hopefully one day have a society where they're actually sort of like everywhere.
So Anna, you have the distinct disadvantage of going third, so you can answer the question, but I also want to offer you, if there's a critical difference that you want to highlight too, feel free to do that as well.
I think that all of our projects show that that research is definitely not a finite process. There's always questions to explore. I think we can all come away with more avenues to explore within each of our respective projects. And I think what Gabe said is really true, that, I think there's a fine line of how we can apply this information to the greater public. I think you have to be cautious about that. I think, at least with mine, for example, there's a lot I could see that could be applicable to maybe clinical music therapy practices, but I think that we still don't have the full picture yet. And I think that's something to consider, keeping that balance in scientific research of what are the answers to your questions, but then also keeping in mind what questions aren't answered. So it's that whole picture.
The known and the unknown.
Yeah,
great.
Absolutely.
Let me open up to participants too. Are there any questions that you want to ask sort of the full group, sort of common challenges that they faced, or think ways that you make sense of how these fit together?
No, I'll just start off with a comment. I thought it was really, really awesome personally. Being able to see how interdisciplinary and how each of your projects pulled from all these different fields, and how much it's necessary, I think, in this time of age too, with like everything kind of being integrative. So I thought that you all did a fabulous job of doing that. And also a pattern that I saw throughout your 3 presentations was exactly that application to the real world, and also the fact that all 3 of your projects do essentially impact society, like directly, with Anna's working with the patients and seeing how in clinical settings potentially, and then Gabe with like literally how you mentioned the Starbucks incident, like that, the need for trainings, and Clayton with your machine learning, with the self-driving cars, like all 3 of them I think are really important. It was really cool to have the opportunity to hear from all 3 of you. So.
Thank you.
If there are no questions, the way I'm going to end is that following Yuna's lead is to go around and say one thing that you've learned or will take away from the presentations today. So Christina's okay if I go to you next?
Sure. I think what I'm taking away from this is just the fact that, so just the variety of different things that are coming up in the world and things that I can be aware of, so I've learned quite a bit. But also on top of that, that each of you really discussed and contextualized it as far as its meaning to the culture and being aware of the biases that are implemented, whether it's through math or whether it's through people, or I missed the first part of yours, but through music or the ways that it impacts people individually. So I thought that was, it's nice to hear students still contextualize it and put it within a culture and talk about it that way.
Okay, we go back here.
Sure. For me, at least, as someone whose relationship with technology is just using it, I am not a CS kid or anything like that. But for what you guys have been talking about, it made me think of how the way in which we're learning and the interconnectivity of the world is actually making it necessary to have all of these conversations and this research going on of, like, when we're thinking of where do racial biases come from, like, when there was less technology, less, like, you didn't have the internet, things like that, it was very much more like, okay, what's at home? What are the encounters that people are having? What are people reading in newspapers? But now that everyone is kind of personalizing their way of educating themselves, I think being able to kind of track it, as Clayton is doing with the machine learning, like being able to track and map how people are essentially coming to whatever conclusions they may be having about, you know, anything from music to like different groups to their own understanding of how technologies impact our lives. I just think it's really interesting how these research methods wouldn't have been possible nor were as important as they are today. And I imagine that they're just going to grow in their importance.
Good point.
I thought it was really interesting how you all managed to, you all did very like specific research, and I thought it was really fantastic how you managed to put it in like a larger and more critical context, because I'm pretty sure that when you were working on this research, you were very like tied down with very small details and, Clayton's case, like mathematical things and, research data, and I was just like really impressed with how you all managed to put it into like a more lay context and in sort of relate it to work being done in society as a whole.
I was impressed by the different perspectives taken for the problems. Like it was really neat how like two of them was just like coming at the problems that I would not have thought were applicable from like a cognitive perspective. It's a really cool, like direct approach to it.
Great. Are there any concluding words you'd like to say or questions that you have for us?
I think one thing which was funny for me with being on this panel is that when I first saw the list of the panels, like, okay, so I guess like we're the only STEM people who applied to TIA, so they put us all together. I guess that makes sense. But I think one of the most fun things has been, even though it felt like at first that we are coming from very different backgrounds and coming from very different fields, realizing how much overlap there was between our research and realizing how many commonalities there were as being like 3 seniors trying to learn what research is and learn how to be involved in it. So I think that was, I think for me, I think that was one of the most impactful parts, is realizing that even though it seemed like we were very separate at first, that there were a lot of overlaps and there were a lot of commonalities between our work.
Mm-hmm. Yeah, going off of that many, like, we all implemented very different methodologies, but I think at the same time we're all coming together to, I guess, try to address questions that pertain to our culture and, us as humans. So I think it's really interesting to see how very seemingly different fields at Brown, we all have very similar questions underlying the research that we do.
I would say that, at least from my own experience working on this with Clayton and Anna, it definitely ignited and amplified my passion to continuing learning more about these topics, because I definitely feel like it's like incomplete, and I definitely like want to like complete it, but not just like my own, but also like supporting other people in their own initiatives, because I feel like oftentimes a lot of this research and a lot of the work is done in silos, and it's not necessarily because it's intentional. Like I don't want anyone to be. It's just that it's very difficult sometimes for people to know that this work is coming, like being done, or like how to feel like people can fit along with those projects. And so for me, at least, I think it's like recognizing how to like learn more about topics that I may not be that I might be unfamiliar with, and then trying to figure out how I might fit into that. But also being more comfortable in discussing these like theories with people who may not necessarily be in the field, because I've also noticed that like many of the people in the class, well, because like a requirement, are people who have like social justice passions and also familiarity with neuroscience. But I am curious to know how the conversations and the explorations and the analysis would be different if they were non-neuroscience people, because if you think about it, if these are going to be applied topics, people who are not familiar with the subjects would also be accessing them and wanting to learn for it. So it's definitely one of the things that I want to try to learn, to be more inclusive, but also to like make sure that it's sustainable and not just like a class that I take.
So one of my favorite events that I facilitated with faculty was to randomly assign faculty to groups of 3, but pretend it wasn't randomly assigned and say, tell us why you think we put you together. And they came up with the best rationalizations. And as you said, Clayton, it may be that you're the only 3 STEM folks, but I think thinking about the alignment between your presentations, you all did a fantastic job. And I would encourage you to think about perhaps a future collaborative publication, thinking out in the future planning a course together. I do think there's a really interesting interdisciplinary resonances in the questions you're asking. So thank you. Just a final round of applause for everyone.
Feel free to grab as much as you like.